In the lesson today, we are going to be exploring what happens when a charge, such as a proton or an electron, moves through a magnetic field. And this will conclude then our unit on electrical and magnetic fields. Due to the COVID timeline, we are not going to be exploring moving charges through electric fields. So we are just going to be doing magnetic fields only. So recall that magnetic field is the symbol B. And recall that when electric current is flowing through a wire, and that wire is exposed to a magnetic field, it will experience a magnetic force, FB. And recall that the direction of the force is always perpendicular to the field, and it's also a three-dimensional direction. And we had our system of right-hand rules to get the direction. So because it is perpendicular to the wire, the magnetic field, we have to look at a component of the magnetic field that is perpendicular to the current. So the magnetic force, FB, the magnetic force multiplied by the current, I, multiplied by the length. Again. Okay. So FB equals magnetic field B times the current I times the length L multiplied by sine theta. That was our magnetic force. The direction of the magnetic force is given by the third right-hand rule. Remember that the thumb direction of the current, fingers direction of the magnetic field, and the palm was the direction of the magnetic force. So for example, if your thumb, if the current was going into the page and the magnetic field was due north, then your palm should be facing to the right, and that would be the direction of the magnetic force. So example one is just a review from grade 11, force on a current carrying wire. You need the field, you need the current, and you need the length in meters, and then you need sine of the angle. So I'll leave example one for you to do. Just make sure you convert the length to meters by dividing 100. So let's talk about now a moving charge through a magnetic field, because of course current is moving charges through a wire. So if a single charge or a beam of charges is moving in a magnetic field, then it will experience a magnetic force. So recall that the direction of electric current, so I, electric current equals number of charges, Q, divided by T. Consider the length, the distance the particles move through the field, length would equal the displacement of the charges. So if the magnetic force acting on a wire is equal to field times current times length times sine theta, the magnetic force acting on a singular charge will equal B field times Q, the charge, times the speed of the charge times sine theta. And typically we rewrite it as such. Magnetic force, FB, equals Q times the speed of the charge times the field times sine theta. So this would be the important formula for the magnetic force acting on a single charge. FB equals Q times V times B times sine theta. When not stated, we assume the velocity is perpendicular. 90 is, theta is 90, sine 90 is 1. So we have the fourth right-hand rule for the direction of a charged particle, the direction of a magnetic force acting on a movement of a charged particle. So the fingertips equals the magnetic field. The thumb represents the direction of motion of the charge, and the magnetic force would be the direction of the palm. So we've got the magnetic field, we've got the direction of motion of charge, and we've got the magnetic force. I should move this over here, and the palm of the hand would equal the magnetic force. Okay. To get the directions for a negatively charged particle, we simply use the opposite directions from right-hand rule number 4. So right-hand rule number 4, no, I'll put this here in red. Right-hand rule 4, number 4, is based on a positive charge. So if it's a positive charge, then you use right-hand rule, and if it's negative charge, then you use the right-hand rule, and then your final answer, you take the opposite direction. So for example, if we have a proton moving into the page, your thumb should be pointing down into the table. If the field is going north, then the proton experiences a force to the right. Now, if it's an electron, negative charge, moving into the page with a field going north, you would put your thumb into the page, you'd put your fingers pointing north. Now your palm is pointing to the right, but because it's a negative charge, you do the opposite of right, which is left, and therefore an electron would experience a force to the left. A proton is moving at 65% the speed of light to the right, enters a field 70.75 Tesla into the page. What is the magnitude and direction of the force acting on the proton? And we will get the vectors. So first of all, the speed in this case equals c, the speed of light, which is speed is 65% or 0.65 the speed of light, which is c. Now c is a constant term, and that value is 3.0 times 10 to the power of 8 meters per second. So that is the speed of light, c. Make sure you are aware of that. So first things first, we'll get our speed. So we'll go 0.65 times the speed of light. So times 3 times 10 to the power of 8. 5 times 3 times 10 to the power of 8 gives us 1.95 times 10 to the power of 8. 1.5 times 10 to the power of 8 meters per second. Good. So the force equals QVB times sine theta. Nothing is stated about theta, so we're going to assume theta is 90 degrees. And therefore sine 90 is 1. So F is going to equal Q, which is a proton. So remember the proton is the charge E, so 1.602 times 10 to the power of negative 19 times V, which is 1.95 times 10 to the power of 8 times the field, which is 0.75. So we do the plug and chug on the calculator. So we already have that in, times 1.602 times 10 to the power of negative 19 times 0.75. And we get a force that is 2.34 times 10 to the negative 11. 4 times 10 to the power of negative 11 newtons. Now, direction. The speed is to the right, so you have to make your thumb go to the right. The field is into the page, so while your thumb is to the right, you have to rotate your hand. Your hand has to go into the table, and you'll notice that your palm is pointing due north. Thumb is to the right for the speed. The field is into the page, the fingers into the page, and your palm is pointing due north. So that would be the direction of the force, north. And it would be north because it is a proton. If this was an electron, then the direction would be south. So that's a very specific, overview example of how to use the force QVB sine theta to solve for the magnetic force acting on a moving charge in a magnetic field. So now, direction. Because the force acting on the proton in this case, it is perpendicular to the velocity, the proton then will show circular motion. Okay, so recall from your circular motion unit, the simplest definition of centripetal force is Fc equals m, certain equation, m times v squared over r. And the magnetic force is equal to QVB times sine theta. So if these two are equal, then of course it's going to show that this particle is going to move in a circle or an arc. So if these two are equal, then we get the following. So mv squared over r equals QVB sine theta, and we'll just say it's 90 degrees, so sine 90 is 1. You'll notice that there's v squared on the left and v on the right, so that v cancels. So we're left with mv over r equals qb. And lastly, we could state it as this, and this is going to be a very important relationship for us. If we multiply the r up, mv equals q times field b times r. That's the radius. So this is a very important relationship for the motion of charged particles in a magnetic field. We can use this relationship to solve for m, to solve for v, to solve for q, to solve for b, or to solve for r. So very useful relationship here. So make sure that's the one that you have down. And so it's a matter of just plugging and chugging. Always remember that m is in kilograms, v is in meters per second, q is in coulombs, and r is in meters. So particle has the mass, it has a charge of -7e, so notice it's a negative charge. It accelerates to a velocity v and enters a field region. What is the radius of the curve of the path of the electron? So r would equal mv divided by qb. So r would equal mv divided by q times b. So the only thing we don't know is q in coulombs. So q equals 7 times 1.602 times 10 to the negative 19 coulombs. Get that number. 7 times 1.602 times 10 to the power of negative 19 coulombs. 1.12 times 10 to the negative 18. Good. So that's important. So now to solve for r. So r will equal m, which is 8.84 times 10 to the power of negative 30 times v, which is 5.4 10 to the power of 6 meters per second, divided by q, 1.12 times 10 to the power of negative 18 coulombs, times the field, which is 0.94 Tesla. Plug and chug on that, and I think it says 1.12, sorry. Okay, calculator. So 8.84 times 10 to the power of negative 30 times 5.4 times 10 to the power of 6, and then divide that by 1.12 times 10 to the power of negative 18 times 0.94. And you get 4.53 times 10 to the negative 5 meters. 4.53 times 10 to the power of negative 5 meters. And that would be the answer. Again, we can use this relationship to solve for any one of the variables. And we won't worry about the potential difference because we didn't cover off the electric field, so that'll strike through that. So for example 4, we have an oxide anion, has mass of that amount, it's traveling at that speed, enters a region of magnetic field. the ion moves in a radius, what is the magnitude and direction of the magnetic field? And note that it's a negative charge. So we will have to make sure that our direction, we take the opposite of the direction from right-hand rule number 4. So we're solving, we'll bring this down here, copy that. So that's our relationship. So we're solving for B. B in this case is going to equal MV divided by QR. So we have to find our M, and we need our Q, and then we have our V, and we have our R. Okay, so M is going to equal that number, so we better get that value. So it's 16 times 1.67 times 10 to the power of negative 27, which gives us 2.67 times 10 to the negative 26.